Your fridge, your air conditioner, the cold chain that keeps your medicine alive. Every single one of them runs on a technology that hasn't fundamentally changed in over 100 years. And here's the part nobody tells you. The gas hiding inside those machines is quietly warming the planet thousands of times faster than the carbon coming out of your car. Now, China is racing to replace all of it with something that has no gas, no compressor, and makes almost no sound at all, just metal and magnets. The problem? The material this whole revolution depends on? China already controls almost all of it. And that changes everything. Before we get into it, if you love understanding where Chinese technology is actually heading, hit subscribe. This one is going to reshape how you see your own kitchen. Let me explain how your fridge actually works, because once you see it, you can't unsee it. Every fridge, every AC, every walk-in freezer runs on the same trick. You take a gas, you squeeze it hard with a compressor, and squeezing it makes it hot. Then you let that hot gas flow through coils on the back of the fridge, where it dumps its heat into your kitchen. Then you let the gas expand again, and expanding makes it cold. That cold gas loops back inside and pulls the heat out of your food. Squeeze, dump, expand, absorb. Over and over, forever. That low humming sound you hear at night? That's the compressor doing this dance. It's a genuinely brilliant idea. Simple, cheap, reliable. But it has one flaw that we ignored for a century. The gases doing the work, the refrigerants, are some of the most powerful greenhouse gases ever created. We're talking about HFCs, hydrofluorocarbons. And a single tiny leak of these gases doesn't just warm the planet a little, it warms it thousands of times more aggressively than the same amount of carbon dioxide. So while we were busy inventing cold, we were quietly cooking the atmosphere. And here's the frustrating part. Every improvement we've made for decades, better insulation, smarter thermostats, more efficient motors, none of it touches the core problem. The gas is still there. The compressor is still there. The noise is still there. And the scale of this is bigger than most people realize. Cooling isn't a small corner of our energy use. Think about it. Every home fridge, every office AC, every supermarket freezer aisle, every hospital, and increasingly every data center full of servers that would literally melt without constant cooling. As the planet gets hotter and more of the world gets air conditioning for the first time, our demand for cold is climbing fast. Which is a strange trap when you think about it. The hotter it gets, the more we cool. The more we cool, the more of these gases leak out, and the hotter it gets. We built ourselves a loop that feeds itself. So engineers around the world started asking a wild question. What if you could create cold without any gas at all? No squeezing, no leaking, no 100-year-old compressor. And it turns out the answer isn't hiding in a better liquid. It's hiding inside solid metal. This is where it gets strange. Okay, so how on earth does a magnet make something cold? This sounds like magic. It isn't. It's one of the most beautiful pieces of physics you'll ever hear, and I promise I'll keep it simple. Take a special metal. The classic example is gadolinium, a silvery rare earth metal. Inside that metal, every atom acts like a tiny compass needle. Normally, those little needles point in random, messy directions. Now, bring a strong magnet close. Suddenly, all those messy little atomic compasses snap into line, all pointing the same way. And here's the key. When they get organized like that, the metal releases energy as heat. The block of metal literally warms up just from being magnetized. Then, you pull the magnet away. The atoms lose their marching orders and fall back into chaos. And to fall back into that messy state, they have to pull energy in from their surroundings. So the metal gets cold. Genuinely cold. Cold enough to chill the air or the water around it. That's it. That's the whole secret. It's called the magnetocaloric effect, and scientists have actually known about it since 1881. No gas, no compressor, no leaks, almost no sound. Think of it like a sponge, but for heat instead of water. Magnetize it, and you squeeze the heat out. Demagnetize it, and it soaks the heat back up. The magnet is just your hand, squeezing and releasing. And there's a reason this matters so much beyond just being clever. There's no gas that can leak, so there's nothing to warm the planet. The solid metal doing the work has what scientists call a global warming potential of 0. And because there's no compressor slamming away, there's almost nothing to make noise or wear out. Fewer moving parts means a machine that could, in theory, run for decades in near silence. For over a century, this was a laboratory curiosity. Cool in theory, useless in practice, because the temperature swings were tiny, a few degrees at best, and the materials that gave a big effect tended to wear themselves out fast. There's a problem scientists call hysteresis. Basically, the material getting sloppy and losing energy every cycle, degrading a little more each time until it stops working well. So for decades, you had a cruel trade-off. Materials that cooled powerfully didn't last, and materials that lasted didn't cool much. But recently, that changed. In labs from Japan to Germany, researchers finally started cracking the materials problem, discovering new metal recipes that swing temperature harder and survive the endless cycling without falling apart. One recent breakthrough more than doubled the usable cooling effect of a material while keeping it stable cycle after cycle. And the moment those pieces started clicking into place, the race to own this technology began. And one country had a massive head start. For years, the leaders in this weren't in China. They were in America and Europe. In the United States, at the Ames Laboratory in Iowa, researchers built one of the first magnetic cooling machines that could genuinely compete with a normal fridge. The heart of it is a device with a mouthful of a name, an active magnetic regenerator. Picture a set of beds packed with tiny particles of magnetocaloric metal and a big disk of permanent magnets spinning above them. Every time a magnet sweeps over a bed, that bed heats up. As it sweeps away, the bed cools down. Water, laced with an anti-rust additive, flows between them, grabbing the heat and hauling it away. And in Europe, this went from lab bench to store shelf. A German company built a fully commercial magnetic cooling unit, completely silent, running purely on magnetism. Another company, at a major refrigeration trade show, literally served people cold drinks straight out of a working magnetic fridge, right there on the floor. Not a slideshow, not a promise. A real machine handing you a cold soda. Their targets aren't just kitchen fridges. They're going after supermarkets, hospitals, and data centers. The places where cooling has to run 24 hours a day and the electricity bills are brutal. But here's the twist that turns this from a science story into a geopolitics story. All of these machines, the American prototypes, the German products, every single one of them needs two things China happens to sit on top of: strong permanent magnets and rare earth cooling metals. And that's the part the West is only now waking up to. You can invent the coolest fridge in the world, but if you can't get the magnets or the metal to build it at scale, you don't actually own the future. You're just renting it. So let's talk about the country that owns the raw materials and what it's now doing with them. Here's the fact that reframes this entire video. Magnetic cooling doesn't run on magic. It runs on rare earth elements, and China controls the rare earth world almost completely. Let me give you the real numbers because they're staggering. China mines around 69% of the world's rare earths, but mining is the easy part. The hard part is processing and refining them, and there, China handles roughly 90% of it. And when it comes to actually manufacturing the high-performance permanent magnets, the exact magnets a magnetic fridge needs, China makes somewhere between 90 and 94% of the global supply. Now look at what export controls on 7 rare earth elements, and gadolinium was on that list. Not by accident. Magnets we're talking about aren't just in fridges. They're in electric car motors, wind turbines, smartphone speakers, MRI machines, and deep in military hardware. A single advanced fighter jet contains hundreds of pounds of rare earth material. So when China adjusts the flow of these elements, it isn't just nudging the price of future refrigerators. It's touching the nerve center of modern industry and defense all at once. Cooling just happens to be the next domino. So this is no longer just a story about a cooler fridge. It's a story about who controls the physical building blocks of the next century of cooling. The West can design the machine, but right now, China holds the metal, the magnets, and the factories. And Chinese labs aren't sitting still either. Their universities and research institutes, from the Chinese Academy of Sciences to major technical universities, are pouring effort into new magnetocaloric materials and into integrating the whole system from raw ore in the ground all the way to the finished cooling device. That's the part that should really get your attention. It's one thing to hold the raw materials. It's another to also be racing to build the finished product on top of them. Which brings us to the real question: what happens next? Now, before anyone panics or celebrates, let me be honest about where this actually stands. Magnetic cooling is not going to replace your fridge next year. There are real, stubborn hurdles. The first is the magnets themselves. To get a strong enough cooling effect, you need seriously powerful magnetic fields, more than 1 Tesla, which is far beyond a fridge magnet. And those high-grade permanent magnets are expensive and in fierce demand from other industries: electric car motors, wind turbines, missiles, MRI machines. Everybody wants the same magnets. So the raw material isn't just controlled by one country, it's also fought over by a dozen industries at once. The second hurdle is size and cost. Right now, these systems are bulky and pricey. Shrinking them down cheap enough to sit in your kitchen is genuinely hard engineering. And there's a rival technology snapping at its heels. It's called elastocaloric cooling. And instead of magnets, it uses mechanical stress. You physically stretch or squeeze a special metal, and that makes it heat and cool. On paper, it can be a little more efficient, and it skips the rare earth magnet problem entirely. But it has a weakness. Constantly stressing metal wears it out over time, like bending a paperclip back and forth until it snaps. So magnetic cooling's biggest advantage is durability. No metal fatigue, no snapping. It just quietly runs and runs. That's exactly why it's so attractive for hospitals and data centers. Places where a cooling failure isn't an inconvenience, it's a disaster. And the whole global market is exploding. Analysts expect magnetic refrigeration to grow from a couple $100 million in 2025 to over $1 billion by 2030. That's the kind of growth that turns a laboratory curiosity into an industrial gold rush. So the path forward is clear. Whoever makes the materials cheaper, especially that lanthanum iron silicon alloy, and whoever locks down the magnet supply, wins. And on both of those fronts, one country is already sitting on the finish line before the race has really begun. So let's zoom out and imagine the world this actually builds. Picture a fridge that makes no sound at all. No hum, no buzz, no rattle at 3 in the morning. An air conditioner that cools your whole apartment in total silence, with no gas that can ever leak into the sky. A cold chain that carries vaccines across continents without a single greenhouse molecule escaping. That's not science fiction. That's what a mature magnetic cooling world looks like. The likely order of arrival goes like this. First, the big industrial players, the supermarkets, the hospitals, the data centers, swap their old gas systems for silent magnetism because they feel the electricity bills and the regulations first. Then, as the materials get cheaper and the machines shrink, it works its way down into our homes. But here's the thought I want to leave you with. The country that ends up controlling this isn't necessarily the one that invents the best machine. It's the one that controls the metal and the magnets underneath it. And today, that's China, holding roughly 90% of the processing and the magnet making that this entire technology stands on. So the next time you open your fridge and hear that familiar hum, remember, you're listening to 100-year-old technology on its way out. The future of cold is silent, it's solid, it's magnetic. And the race to own it is one of the quietest, most important contests of our time. Most people will never notice it happening. But now, you will. If this changed how you see something as ordinary as your fridge, that's exactly why this channel exists. To show you the quiet ways Chinese technology is reshaping the world you live in every single day. So here's my question for you. Would you trust a fridge with no gas and no compressor, running purely on magnets? Drop your answer in the comments. I read them, and I'm genuinely curious where you land.